All right, welcome. In this video, we are talking about sampling proportions or sampling distributions of sample proportions. So far, lesson 4.4 has talked about sampling distributions of sample means, but now we're talking about proportions. So remember, a proportion is like a percentage. It is like a fraction type of a thing. So it's not a mean. Instead, it's like a percentage. So if we have repeated random samples of size n that are taken from the population, where it's qualitative data. So the key for here is that it is qualitative data. So right here we've got qualitative data instead of quantitative data. Then the proportion of interest is p. All right. And the mean of all the sample proportions is mu sub p hat. All right. Or mu of p hat. And what we know about these two things is these two things would be equal. So here is the formula for the mean of a sampling distribution of sample proportions. So the mean is equal to the proportion of the population. All right, the next super important formula we want to talk about is that standard deviation. So the standard deviation would be the square root of p times q divided by n, where q is 1 minus p. Okay, but this only works as long as n times p is greater than 10 and n times q is greater than or equal to 10. So right here is what we have to know. So there's a lot of words up here that I didn't read to you, but this is like the key. This is what we have to know. That's something that I would jot down in my notebook. Okay, also, this is the next thing that shows up in those notes. It compares the means, the sample means to the sample proportions. So biggest difference here is sample means is quantitative, sample proportions is qualitative. Okay, and then we've got how would we find our centers, which is our means. So the mean equals the mean, and then the mean equals the proportion. Our spreads, which is our standard deviation, right? Standard deviation goes there. And then this is to decide, is it normal? So is it normal? That's what you need to check to decide if your population is in fact normal. So we are focusing in this video on if n times p is greater than or equal to 10 and n times q is greater than or equal to 10. So if we are given an example that 60% of all American students who attend college are females, in our first scenario, we had 120 samples of size 50. So for this example, n is your sample size. So n equals the sample size, which means n would equal 50. P equals the proportion of success. Okay, well, what does that mean? That means it's the proportion basically that they give you. So my proportion, remember proportion is kind of like a percentage, is 60%. So P would be 0.60. Q is the proportion of failure. So proportion of failure is the same thing. Well, not the same thing, but proportion of failure and proportion of success, they are complements of one another, which means they have to add up to 1. So in order to find Q, you do 1 minus P. So in this case, we would do 1 minus 0.60, which would give us 0.40. So Q is 0.40. So the first thing we need to do is check to see if the distribution is normal. So in order to check to see if the distribution is normal, that's where we are using these little formulas up here. So n times p, let's see, n times p. Let's see, n was 50, p was 0.60. So what is 50 times 0.6? Is 30. So is 30 greater than or equal to 10? So if I have 30 over here, is this greater than or equal to 10? Check. Yes, it is. So now I got to do n times q. So n times q would be 50 times 0.4. Well, 50 times 0.4 is 20. So is 20 greater than or equal to 10? Check. Yes, it is. So since n times p is greater than 10 and n times q is greater than 10, we can say that yes, this is normal. So yes, it is approximately normal. Okay, so now that means that we conclude that p hat is approximately a normal distribution with our mean. Remember, our mean of p hat is equal to p. Well, what was p? Up here we said that p was 0.6, so our mean is 0.60. Okay, we want to find the standard deviation as well. So standard deviation formula is right here. So we have the standard deviation of p hat equals the square root of p times q divided by n. So square root p was 0.6, q was 0.4, n was 50. So when I plug this into my calculator, I really want to make sure I'm doing 0.6 times 0.4 divided by 50 and then taking the square root of that whole thing. So I use parentheses all the time. So I would hit my square root button and then open some parentheses and do 0.6 times 0.4 divided by 50 and then close your parentheses. That's how I would do this one. And I got my standard deviation is 0.069. Now, to find the approximation for samples of size 250, is the standard deviation close to the standard error found in the simulation? So my standard error was 0.03. So for this one, if my sample size is 250 instead of 50, I'm still using that standard deviation formula. So square root of p times q over n. But now I still have 0.6 times 0.4 divided by now 250 instead of divided by 50. And when I plug all that into my calculator, I got 0.0309, which would be 0.031. So are these close? Yes, they are. All right, and that's going to be it for this video. In the next one, I will talk about putting these onto that normal distribution curve. Let me know if you've got any questions.